We'll now have Felix Eigenbrod presenting outcomes on spatial and temporal scaling specifically. We will not take any questions after Felix' talk, and then we'll then have questions together for Paula and Felix after both of them are presented. Thank you very much. Felix, it's your turn.
Thank you very much, Victoria. Can everyone hear me?
Yes.
Thank you very much, Victoria. It's great that we've got already such good engagement. I'll try to speed things up a little bit just to keep us moving along. So as has already been mentioned, this is Peter, Paula and I are doing is a bit of follow-up on what happened last summer. We're trying to synthesize some of the sort of things that emerged from last year. And obviously all of these things are related to each other. So I'm going to be talking about scale in decision making. Just going to very briefly, ask what do we actually mean by scale? So scale has multiple definitions. I thought it'd be quite useful to go through some of the ones that are what I actually mean when we talk about scale. So one very important aspect of scale is what's known as measurement scale. So spatial or temporal extent and resolution. So by example, you could have a study that covers a bit of Scotland, one that covers all of Britain, or one that covers the world. Those are different spatial extent. Or we could have spatial resolution, which tends to be applicable to raster data set. It's another word for that would be granularity or the grain size. So you could have 1 kilometer data on the left, 1 by 1 kilometer data, or 10 by 10 kilometer data, in this case, for forests in Eastern Europe. And again, that can apply in space as in time windows, space windows. And another aspect of scale is what the ecologists or landscape ecologists call phenomenological scale, which is essentially at what scale does a particular process or organism operate at. So for example, from this paper here, this is an example from ecology, you might have some small rodent that interacts with, that forages at quite a local scale, maybe 1 or 2 kilometers from some focal point, but disperses, so the young moving across the landscape at 4 kilometers, a much larger spatial resolution. In that case, the scale of effect of the foraging habitat is considerably smaller than the scale of effect of matrix quality, which is the non-habitat aspect of the landscape. And I think this phenomenological scale is quite a useful concept. I think it applies equally to sort of socio-ecological systems like landscapes as to particular individual organisms. You can think of people's scale of day-to-day dog walking is probably a couple hundred meters where they live, but their scale of where they go for holidays in landscapes might be hundreds of kilometers, but much less frequently and much more sort of, just for that annual trip to the Lake District or what will you. And of course, any water-related process operates at a different phenomenological scale. And you've got catchments and all the rest of that sort of thing. So phenomenological scales are not necessarily, they sometimes the same scales at which landscapes are managed, but not necessarily. If you've got, so administrative units might not align to how people actually move, or they might, but they might well not align to, and certainly a single administrative unit is unlikely to capture all the phenomenological scales that matter for managing landscapes. So why is scale such an issue? Well, the big problem that we have is something what the geographers call the modifiable areal unit problem, or MAUP, which is simply saying that patterns and therefore processes observed at one scale will vary depending on the scale of observation. And statistical relationships and hence inference will also vary. So this is a very simple example from about 2 different things. So this is even more of an issue if we're talking about trade-offs, which in landscapes you almost inevitably are. So on the left here, we have a landscape where we're working, where we've got, let's say, 1 by 1 kilometer resolution land cover data. And here we've got trade-offs between cropland production and forestry. The 2 never occur within the same 1 by 1 kilometer pixel. But if we suddenly run our analysis at 4 by 4 kilometer resolution, voila, we have synergy. We've got both forestry and cropland within the same management unit. So that's a simple example of the MAUP. Given the MAUP, changing spatial resolutions, what's known as upscaling, or downscaling, so going from finer resolution to coarser resolution, and the other way around, can be quite tricky. However, moving between scales is necessary if we're interested in managing things, because we have to sort of make some sort of harmonization of data. If we're going to understand trade-offs, if we understand, we have to somehow operate with these different phenomenological scales, and sort of link these together in the models that we're working with. So what Paula and Peter Chandler, as well as Peter Cox and I did, is after the last series of workshops, we did a little bit of work on key research priorities. And we tried to organize them into things we thought would be solved in the short, medium, and longer term. I'm just going to go through some of the stuff we came up with on scale. So in the short term, one thing that really emerged last year is that we are very rapidly entering the sort of big data for landscapes. And we have now these things called data cubes, which are from remote sensing, particularly from remote sensing data, where we have a lot of harmonized data for very large extents and across multiple years. So for example, there's now global data from the ESA on land cover at 300 by 300 meter resolution for every year from 1992 to 2015. That's really useful because it increasingly enables us to make causal insights, because we don't just have one snapshot in time, we have space and time. And people have started using these things. So for example, the 2000 to 2012 forest loss data, which is 30 meter resolution, which was processed with Google Earth Engine, and again, the computing revolution has changed what we can do. This paper from Curtis et al. In Science looked at what are the drivers of that loss in forest cover. Is it subsistence agriculture, commercial agriculture, or forestry? So people are starting to think about these sorts of questions, but it's really just in its infancy. So one thing we discussed last year, and something that's probably going to come quite quickly, because we do have these cubes now, is using new mathematical tools. For example, things like dominant frequency state analysis, which come from, for example, from the climate and weather forecasting communities, who've been used to working with these big spatial temporal data sets for longer periods of time. In the medium term, we all thought that developing theory, that we would hopefully make reasonable progress in theory for scale. So upscaling and downscaling requires rigorous theory around scale if we really want to do it well, because there's so many different ways we can upscale or downscale. And such theory is still largely lacking for landscape decisions. But of course, people have been thinking about this. So for example, Bill Coonan, who spoke last year, has been doing this quite a lot, thinking about upscaling for biodiversity. And he's been using ecological theory to show how you can use data collected at a very fine resolution to make inferences about abundance and richness at coarser spatial resolution. So again, some of those ideas about how to develop that theory, I think, could be extended to landscape decisions. So also other things that have come from other parts of the wider literature, such as spatial fusion or Bayesian melding, which are used in air quality modeling, could potentially be used. And perhaps stuff such as emerging constraints, which Peter Cox was obviously instrumental in, from the climate modeling community, could possibly apply to landscape decisions. And could tipping points, this idea that you're going from one state to another state, that there's a sudden rapid change in environmental conditions or one thing or another, such as a lake going from being clear to suddenly anoxic and green, because that's a tipping point in how much pollution has been entered. Could that be done for landscapes? And actually, we discussed this last year, and in the last couple of months, actually, a paper by two people who were here last year, Simon Wilcock and John Deering, and John's PhD student, Greg Cooper, showed with simulations and some empirical data that suggested that that regime shifts, these tipping points, might occur disproportionately faster in larger ecosystems. So beginning to take those ideas that come largely from time to space. And we still have a fundamental understanding of why we have these different phenomenological scales. So we have one big discussion we had with James Bullock last year, is that scale and movement, of course, inherently linked. The phenomenological scale is linked to the movement. So perhaps some of the ideas from movement ecology, from theoretical ecology, could be applied and taken and applied across into landscape decision theory. And longer term, I think there was some discussion that what would be really useful and possibly impossible are parsimonious general models. So I think these get, the idea here is that we really get at some of this structural complexity that Peter was talking about, the structural uncertainty. So if we have simple models and we really understand the issues of scale and these, how it all hangs together, we might be able to predict, for example, land use change over time with relatively simple models, process models or statistical models, where we really understand the drivers and sort of, as such, really understand that structural uncertainty, which is so difficult to deal with, as Peter has discussed. And that I think we're a ways away from that, but that to me seems like it'd be a really useful and exciting future development. And some basic ideas which we talked about this last year, which I think were pretty cool, were what Roddy Dewar was doing with maximum entropy models, combining statistical drift with mechanism and trying to understand, in this case, how simple land use change in savanna systems works. Could that be applied more broadly to other kinds of systems? So many thanks to quite a lot of people who helped me with this in these slides, and to all the participants from last year. That's it for now. Thank you.